So the next little thing that I want to mention in the world of these discrete logarithms is that they actually do behave very nicely. So if I were to look at this log base 2 of 140, what I can see is that that kicked out an answer of 100. That was what we just saw in that last example. What I can also see is that the number 140 actually factors. So this thing turns into a 2 squared times 5 times 7. So if I shove that factorization into this argument of this logarithm, so it's log base 2 of 140, swapping out the 140 for a 2 squared times 5 times 7, what I can see is that our classic collection of properties of logarithms are going to hold steady. The idea here is that logarithms are going to take multiplication and rip it into addition, and then it's going to take those exponents and then fling them out in front. So the idea here is that I get a 2 squared times a 5 times a 7. So the 5s all get lumped together, the 7s get all lumped together, the powers of 2 all get lumped together, and then this little exponent of 2 gets flung out in front of everything. So if you were to compute those 3 little logarithms on their own, so in this case it's still a brute force approach to it, what you can see is that you're going to get an output of 1, you're going to get an output of 104, you're going to get an output of 142, and if you combine all of those things and reduce modulo 148, so again, this logarithm is then defined modulo p minus 1, so it's that weird annoyance. The idea is that we get an infinite number of solutions, but they're all viewed p minus 1. So if you take that output, reduce it modulo p minus 1, or in this case 148, you get back to that answer of 100. So this discrete logarithm is built up in a correct way that's somehow consistent with our continuous logarithm. So all the properties that we know and love about the continuous logarithm are then going to stay somewhat consistent with the discrete case. So the idea is that multiplication turns into addition, exponents get flung out in front. All of those nice properties we're still going to have in the world of the discrete logarithm. So those 2 little facts are actually embedded in this particular remark, or these 2 remarks. The second one is this fact that the logarithm works like a logarithm. That is, it's going to take addition, or it's going to take multiplication and convert it into addition, and it's going to take exponents and then fling them out in front. The part up above is a little bit more formal as to what is this construction of log base g. The idea is that this thing is then going to be viewed modulo p minus 1. This particular statement up here is the exact same bit as when we had one solution and then we added some extra p minus 1 to it. So when we had that original answer of 100 and then we added 148. Well, you can add 148 as many times as you want to, and you're going to constantly get this output of h again. So what that means is that this log base g becomes a function that eats values from this field, and then it's going to return values modulo p minus 1.